Yeah, I can see it.
Right. All right, so a spherical balloon full of helium gas. So the density is 0.164, occupies a total volume of 4.7. It is tethered to the ground by a line. Given that the mass of the rubber balloon before inflation is 0.5, so mass 0 equals 0.5 kilos, and that the density of the surrounding air is 1.2, so density of helium, and then the density of air is 1.2. Calculate the tension in newtons of the line. Okay, so there's some tension due to the buoyancy of the balloon. So I've never done a question like this before. However, what I would do is that I would use physics, the physics that I know, to try and build up a picture, right? Mm-hmm. So what we know of the balloon is that the reason why it's floating. So if we assume that the air surrounding the balloon is a liquid, yeah?
Yes.
So we have a liquid all around here. Okay. Now, whenever an object is, by the way, I'm looking over here because I'm imagining your face there. So
don't worry.
Yeah.
Don't worry, no problem.
What was I saying? So the balloon is immersed inside a liquid, okay? And this liquid happens to be air, right? Any object that is immersed or that is inside a liquid displaces an equal volume of the liquid, yeah?
Yes.
Because the object has displaced a volume of the liquid, there is a pressure surrounding the object due to the displaced volume. Now, because we know that gravity only acts downwards, doesn't it?
Yes.
Okay, so the weight of the object, the weight of the balloon, and the gas inside the balloon is like that, yeah? Mm. But the pressure due to the air all around it is going to be like this. But the only lines that we care about are the ones going straight up, that are directly counteracting gravity, yeah?
Yes.
So the first thing that we should probably write is the quote unquote weight of the balloon, using the Archimedes Principle or buoyancy. So true weight
0.5 times 9.81
equals so if I just write MB, so mass of the balloon times G, take away the weight of the air that has been displaced. Now I can already tell you that the weight of the air that has been displaced is going to be a lot higher than the balloon because of the different densities.
Yes, it is different.
Yeah, we're basically assuming that. So are we basically just assuming that the density of the balloon is effectively 0.164? Occupies a total for. Okay, you know what? We also have to talk about the gas inside the balloon. So the total mass of the balloon is the mass of the balloon plus the mass of the helium gas inside the balloon. Okay, so MB equals the mass of helium plus mass naught, okay? So the mass of helium is going to be its density, so 0.164 multiplied by the volume that it occupied, which is 4.7. And that is going to be added to the mass of the balloon, 0.5. So could you please use a calculator to calculate what that is?
Yeah, sure. Give me a second. So it is 1.2708. 1.27.
37.
27.
1.271 to 3 decimal place kilograms. Okay. So that's the this is the mass of the balloon so far. Now, if we talk about the mass of the air that was displaced due to the volume.
What about the cubic? It's okay, never mind. No, that's fine.
Okay. So the mass of the air is the density of the air multiplied by the volume of air, which is still 4.7. So the mass of air equals 1.2 multiplied by 4.7, the exact same volume that was displaced. And if you could please calculate what that is.
$5.64.
5.464.
5.64, sorry.
5.64 kilograms. Okay. So when we go back to the true weight of the balloon, weight is a force, isn't it?
Yes.
So you will note, you will realize that the resultant force is the resultant weight, which happens to act upwards, and that will be the tension. So the true weight of balloon equals 1.271 G, take away 5.64 G. So if G equals 9.81, could you please calculate what the resultant force is?
It would be minus 42.86.
Okay. Do you agree with the fact that there's a minus?
Yes, I do.
Okay. So what did you say the number was again?
Minus 42.86.
Minus 42.
Mm-hmm.
0.86.
Mm-hmm.
Okay.
If we round it up.
And that should be the answer. Unless you got a different answer for me.
To be honest, I don't know the answers yet. It comes up next week.
Right, okay.
But this is the style of the questions. That's what we have.
Okay. Well, either way, if we always have to go over our questions, and we always have to go over our knowledge, all right? So we use our knowledge in order to build the solution to the question. If our knowledge is wrong, or our knowledge is there's a hole in our knowledge, then of course our solution is wrong. The knowledge that I used was regarding buoyancy. Yeah, do you know, are you familiar with buoyancy?
Not really, but I got what you have done here.
So do you want me to explain what buoyancy is?
Yes, please.
Okay. So if I was to just literally get a YouTube video, for example, buoy in water, buoy floats in water, not buoy as in we're talking about the actual, okay. So just for an example, right? So so this is an example of a buoy.
Yes, I get it.
Right. The reason why it floats in the water is because it has the whole volume that the buoy takes up, right? It has pushed the water out from that volume. And that water is pushing it back. It's trying to push against it. Now, it just so happens that the density of water is very high compared to the density of
air.
Not even air, of this object. This is what, steel or iron or whatever it is. That buoy is probably a mixture of plastic and steel, right? So its total density is probably lower than the density of water. Water is really, really dense. Water is 100 kilograms per meter square. That's really, really dense, right? So when water pushes against you, it will lift you up. And that pressure creates a force that acts against your weight. So the weight of the buoy acting downwards is much less than the weight of the water acting upwards. So the water is winning and keeping it up, keeping it from sinking. Yeah. The actual principle is called the Archimedes Principle. So buoyancy is the effect, but the principle is due to the Archimedes Principle. So if you want to copy this down and maybe,
yeah, I would. That's helpful actually.
Yeah, the Archimedes Principle, right? So if you do some quick reading on it, it will give you some very simple expressions as to why, you know, something like what we've done here makes sense. So I just used the Archimedes Principle to say the balloon is in a sea of air. Okay. Liquids and air are both liquids, as strange as that sounds. I know it sounds strange, even though they are different states of matter, but liquids and air are both liquids, or they are approximated air or gas, sorry, liquid and gases are both liquids. So you can approximate gas to be a liquid. That is why we can use the Archimedes Principle in this situation, because we have approximated the air as a liquid. The balloon is basically the buoy floating in the liquid of air. And because the balloon has a volume, it has pushed out some air from where it was before. The air is trying to push back in, and it ends up lifting it up. And the tension, this tension here, is basically the mass of the balloon take away the mass of the air, everything multiplied by G. And it's negative because it's acting against gravity. So, you know, forces can be negative. It just means that the direction is opposite. That's all it means. Yeah. All right.